This video is going to cover Chapter 3, Section 2, Polynomial Functions of a Higher Degree. Now, this video is only going to do some of the examples. If you need to see more examples done, you can watch last year's video on YouTube. So the first thing we're going to talk about is the end behavior. And when you have an odd degree polynomial, they're going to have the opposite behavior at each end. And if A is a positive value, then the graph is going to fall from left on the left side and it's going to rise to the right. Now, what I mean by an odd degree, I'm talking about, for example, an x to the third, an x to the fifth, an odd number, x to the seventh. So this behavior, when this number in front of x is going to be a positive number, it's going to fall to the left, rise to the right. When it's a negative number in front of x and it's got an odd exponent, this behavior will be the opposite way. It's going to rise to the left and fall to the right. And if you have an even degree polynomial, and then they're going to have the same behavior at each end. And it's going to take on the behavior or look like a parabola graph. So for example, what I mean by an even exponent, x squared, x to the fourth, x to the sixth, and even power. And the coefficient could be any number. It could be a 2, as long as there's a number in front. It doesn't have to be. It could be a 1. Or if it's a negative, negative x squared, negative 3x to the fourth, any negative number. So when it's a positive number in front of that even exponent, it's going to both be rising to the left, rising to the right. And when it's a negative number in front of that variable squared or to the fourth or to the sixth, it'll fall to the left and fall to the right. So fall left, fall right. Now, what we're going to be doing with this end behavior is after we find the zeros, we're going to add in the end behavior to the leftmost zero and the rightmost zero. Now remember, whenever you're looking for the degree of the polynomial, it must be in order from greatest to least. So you're looking for the largest exponent to determine that end behavior. Next, we're going to talk about finding the zeros. Now, zeros are also called the roots, the solutions. They could also be referred to as the x-intercepts. So whenever they ask you to find zeros, roots, or solutions, we'll list it all. Now, if it says to list only the real solutions, then generally we'll just only enter in anything that's not imaginary. But when we're doing our test on this, I'm going to ask you to list all solutions, real and imaginary. So the real roots are actually just going to be your x-intercepts. So if you do get an imaginary solution, it'll be a solution, but it will not be an x-intercept. Now, when we're looking for the zeros, we're either going to have to do the list of possible zeros, like we just saw in 3.4, or I may allow you to use your graphing calculator to find one of the rational zeros. Then you'll have to do synthetic with that rational zero and then bring it down to quadratic, so then you can find the rest of the zeros, whether they're imaginary or irrational. Multiplicity is talking about how many times a root or a solution or a zero occurs. So if it occurs an even amount of times, then the graph is just going to hit the x-axis and it's going to turn around at that point. So it's like a bounce. So, or another way that you can refer to this as a touch and turn. If it only occurs an odd amount of times, then that's actually going to be across through the x-axis. So for example, let's say we actually did our synthetic and then we either solved our polynomial by factoring, completing the square, or quadratic formula. And let's just say the 4 zeros we came up with were x minus 1, x minus 1, x minus 2, x equals 2, x equals 3. So x equal 1, x equal 1, x equal 2, x equal 3. Now notice my 0 here, or this solution, this one occurs 2 times. 2's an even number. So this one has an even multiplicity. So when I go to graph this even multiplicity is going to be like a bounce, or it's going to touch and turn. It's going to touch the x-axis, and then it's going to turn away. Now these other 2 zeros, they only occur 1 time, and 1 is an odd number, so this has an odd multiplicity. So when I go to graph these are going to be like, they're going to cross the x-axis at both of these numbers. So what I'm talking about, the bounce, so let me go ahead and put these 3 zeros on my graph. So here is the x equals 1, and then here's the x equal 2 and 3. So let's just say that our graph was coming in here from the top. It's coming in, it's hitting 1, but it's not going to cross through. It's going to bounce up, and then it's going to come back down, cross through, and then go back up again. It may not have come up from that direction. I just want to show you what I meant by an even multiplicity. Notice it just touched it, came in, touched it, and bounced back up. Whereas these other 2 zeros, they crossed over the x-axis at both of those 0 locations. Let's try to put all of this together. And it wants first to find the end behavior, the zeros, and the multiplicity. Now, I'm going to go ahead and do a list of possible zeros. But if you notice on the slide here, I've already graphed it in Desmos, which is an app that you can get on your iPad to graph something. You can't use your iPads for the test, but I just wanted to show you how I'm going to graph it by hand, and how my graph that I'm going to do by hand is going to look very similar to my Desmos graph. Now, on the test, you will be getting a question where I do not let you use your calculator, and I do not give you one of the zeros. You will have to do the list of possible zeros like you learned in section 4. So remember to find the list of possible zeros. We're going to list the factors. So remember to find the possible zeros. We're going to list the factors of the last term over the factors of the first term. So the factors of the last term, positive and negative 1, positive and negative 2, positive and negative 4, positive and negative 8. And then the first term was just a 1. So essentially, my possible zeros are going to come from negative 1 or positive 1, negative 1 or positive 2, negative or positive 2, negative or positive 4, negative or positive 8. Now remember, the zeros may not be all of those numbers. It may only be 1, and then the other 2 zeros could be irrational, or they could even be imaginary. If you notice, we have a power of 3, so that tells me I'm going to end up with 3 zeros. So what I need to do now is my synthetic division. Now, if you weren't using your calculator, you'd have to start guessing and testing from this list and doing synthetic until you get the one that'll give you a remainder of 0. Well, we've already seen the Desmos graph here, and I can already see that I have 2 rational zeros here, one at negative 2 and one at positive 2. So let me go ahead and do synthetic division with negative 2. And just by doing synthetic one time, I'm going to be able to get my equation down to a quadratic equation. And if it can be factored, I will factor it first. That'll be the fastest. However, if it's not factorable, then I'm going to use quadratic formula. So you bring down the first term, multiply, add the column, multiply, add the column, multiply, and look, I got the remainder of 0. Now, because I keyed it into Desmos, if I did not get a remainder of 0, then I knew I did something wrong. So now let me go ahead and put my variables back. So remember, this is your remainder, your constant, your x squared. Because remember, this is bringing it down 1 power. So now it's something that is quadratic, and I can factor it. This will factor into x minus 2, x plus 2 equals 0. Now remember, this 2 that was up here that I did the synthetic with, this is also a factor. So I can't forget about that one. That one was from the beginning, so x plus 2. So if it asks you to list all of the factors, these are all the factors of that polynomial. But if it says to list the zeros, or the solutions, or the roots, that's when we have to set them equal to 0. So minus 2, x equals negative 2, add the 2, and x equals 2. Now remember, this one was also here. So this solution has a multiplicity of 2, which is even. So remember, when I go to graph this, it's going to be a touch and turn. This one only occurs one time. So it's an odd multiplicity. So this is going to cross the x-axis at positive 2. Now remember, it also had asked for the end behavior. And remember, when it's an odd exponent, and 3 is an odd number, I'm going to fall to the left and rise to the right. Pay attention to this terminology. So falling, it falls to the left, and it's rising to the right. And this is what you're going to attach to the leftmost 0, the falling left, and to the rightmost 0, you're going to add rising to the right. And then what we're going to also need to do is find additional order pairs in between these zeros. Now, I also need to find my y-intercept, but remember, when it's in this polynomial form, my y-intercept is this constant. So my y-intercept is just going to be the order pair 0, negative 8. However, if you wanted to see the work to find the y-intercept, remember what you're doing is setting x equal to 0. So if I take that and plug it into the original, and remember f of x is really just y equals, so 0 cubed plus 2 times 0 squared minus 4 times 0 minus 8. Notice all of this becomes 0, and then 0 minus 8, I get y equals negative 8. So my order pair is 0, negative 8. Now, let me go ahead and start setting up my graph. I'm going to graph it by hand to see if it looks like the Desmos. So let me just put my x and my y-intercept here. And then I'm going to put my zeros on my graph. So remember, I had a 0 over at negative 2 and positive 2. I also have my y-intercept at negative 8. So now what I need to do is I need to figure out some additional points in between the zeros. So let me add in the end behavior as well. So remember, from this 0, it's falling, and then this one is rising. Now remember, at the negative 2 the negative 2, 0, remember it was a multiplicity of 2. So remember, that was a touch and turn. So really all I need to do here is touch and turn and then come down to my y-intercept. Now what I'm going to do is I'm going to find an additional point in between my y-intercept and this 0 of positive 2. So I'm actually going to do synthetic division with a 1 to get an additional order pair. And I can go ahead and do my original, bring down, multiply, add the column, multiply, add the column, multiply, add the column. So my additional order pair is going to be the order pair 1, negative 9. So it actually goes a little bit below, and then it's going to come down here, and then it's going to come up to this other 0. And if you notice on my Desmos graph, it looks pretty much like what I just graphed here. Now, this plugging in a 1, this may not have been actually the lowest point. It might have gone a little bit lower, but I just wanted to see, did it really just touch the y-axis and then go right back up to that last 0, or did it go a little bit lower? And that's why I went ahead and did that. Now, if you didn't want to do synthetic here to get the additional order pair, the other way you could have done it is taken your original equation, and to get the order pair, you could also set x equal to 1 and then follow order of operations. So this is another way, but honestly, I think the synthetic is the faster way. And again, remember, f of x is y. 1 plus 2 minus 4 minus 8, and then work left to right. Y equals negative 1 minus 8, y equals negative 9. So again, you plugged in negative 1 and you got positive 1 and you got negative 9 out. So same order pair that I just did when I did it using synthetic and using that remainder theorem. The slide has the strategies for graphing. What you're going to do is determine the end behavior. Then you're going to find the zeros and the multiplicity. Then you're going to find the y-intercept. And then you're going to plot additional points. So remember to find the y-intercept. If it's in that polynomial form, then all we have to do is look at the constant. If not, we would set x equal to 0 and solve. And then to get additional points, you either use synthetic division, and then once you get the remainder, that would create the y of your order pair. Then that is the remainder theorem. Or you could take the original problem and plug in whatever x value you want for x, where you need to find that additional point. And also remember to pay attention to the multiplicity to make sure that you're understanding if it occurs an even number of times, it'll be a touch and turn. If it's an odd number of times, it'll cross through the x-axis. Now for this next example, I just wanted to show you that this could be a question that you may see on the test where you're not using your calculator because there's not that many possible zeros. So remember, the list of possible zeros, you're going to list the factors of the first term and then the last factors of the last term and then make it into a fraction form. So positive and negative 1, 2, 3, and 6, all over the factors of the first term. And again, your list of possible zeros is really only the numerator. So again, it could either be a negative 1, a positive 1, negative 2, positive 2, negative 3, positive 3, negative 6, or positive 6. Now, notice it's got an x cubed, so know your end behavior is going to fall to the left, rise to the right, and we're only looking for 3 zeros. Now, the 3 zeros could be from this possible list of zeros, or remember, it could be an irrational 0 or even an imaginary. But one of the real zeros will come from this list. Okay, so I'm going to go ahead and start guessing and testing. I'll go ahead and do synthetic with 1. So 1, negative 2, negative 5, 6. Bring down the first term. Multiply, add the column. Multiply, add the column, multiply, remainder is 0. It's now brought down to a quadratic. I'm looking for factors of -6. That will give me -1, and that'll be x minus 3 and x plus 2. Now remember, if it asks you to list the factors, don't forget about this one. And it was opposite sign of what you think. So these are the list of factors. But to find the zeros, you set each one equal to 0. So here you get x equal 1, x equals 3, and x equals -2. Because you would subtract, add on this one. And these are your zeros, and they're also called your x-intercepts. So if it asks you to write as x-intercepts, you would write it as 1, 0, 3, 0, -2, 0. So listed this way, these are zeros, these are factors, these are x-intercepts. Your y-intercept is 0, 6. And again, you could have plugged in a 0. But again, whenever it's in this form, it's just that constant. So you don't have to waste time plugging in x equals 0. So let me go ahead and put these 3 zeros on my graph. I've got one at -2, one at +1, one at +3. And then also my y-intercept, 1, 2, 3, 4, 5, 6. Okay, let me add in the end behavior. So on this far left 0, falling left, and over here, rising to the right. Now, what I need to do is I need to find additional zeros. Now, notice all of my zeros only occurred one time. So all of these zeros have an odd multiplicity. So at each one of these, it's going to cross through the x-axis. So now what I need to do, though, is I need to find an additional order pair in this section and then another one in this section. So again, you can either plug in an x value into the original, but I'm going to use the remainder theorem, and I'm going to plug in -1, and then I'm also going to plug in +2. And this is going to give me the 2 additional order pairs that I need in order to graph this polynomial. So I'm using the coefficients of the original problem. So bring down, multiply, add the column, multiply, add the column, multiply, add the column. So my additional order pair is -1 and +8. Bring down, multiply, add the column, multiply, add the column, multiply, add the column. So +2, -4. So let me go ahead and add these in. This will tell me how my graph is going to wiggle, and I'll go ahead and connect everything. So -1 and +8. So my additional point will be up above here, so maybe about here. So if I come on from this 0 on up, and then now I come down to that 0, and then the other point I found was 2, -4, and it's about here. So then come down to here, and then bounce back up. Now, this point that's here, and this additional point, it may not be as high as my graph goes, or as low as it goes on the other one. But again, I just wanted to see the general direction of the flow of my graph. Now this slide actually has the graph of what I just did. And remember, the order pair I plugged in was -1 and I got 8. Notice the highest point it was plugging in a -0.786, and then you get 8.2, which is pretty close to what I did. And then same thing here. When I plugged in 2, I got -4. And the lowest point it got was the -4.061. So my graph was pretty accurate without actually plugging in that precise decimal. Skip over example 3. It's just a more repeat of what I've already done. Now, the only difference in this graph versus examples 1 and 2 is example 4, my end behavior is going to be opposite. So for this one, because it's a negative x cubed, it's going to rise to the left and fall to the right once I get all of my information. So again, you would do your list of possible zeros. Now, 20's got quite a few factors. This may not be a question that I would give you without using a calculator, because we would have to list positive and negative 1, positive and negative 2, 4, 5, 10, and 20. And then that's all over. Luckily, it's just 1. So that would be quite a few zeros that we would have to check. 12 different zeros. So this could potentially be a calculator question where you would get one of the rational zeros and then do synthetic. So after you determine that end behavior, everything else is the same. You would guess and test using that list of possible zeros until you find a zero that gives you a remainder of 0, and then try to keep breaking it down till it's quadratic. Luckily, you'd only have to do synthetic one time to get it down to a quadratic equation. So I'm going to go ahead and continue on and do example 5. So this would be a good non-calculator question. So for example, my possible zeros, my factors of my last term is just 1 times 5. So positive and negative 1 and 5 over positive and negative 1. So a possible zero is either negative 1, positive 1, negative 5, positive 5. So notice it's a positive x cubed, so it's going to fall left, rise right for my end behavior. So now what I need to do is start doing synthetic division, and there's only 4 choices. So let me go ahead and I'll start with 1. Let's go ahead and put in the coefficients. Bring down the first term, multiply, add the column, multiply, add the column, multiply. And look at that, I got lucky, I got a remainder of 0. So now I can turn this into a quadratic equation. X squared minus 3x minus 5 equals 0. Notice there are no factors of 5 that will give me negative 3. So this is where I need to do quadratic formula. So x is equal to opposite of b, negative b, or b squared minus 4ac, all divided by 2 times a. So x is equal to 3 plus or minus 9 plus 20 over 2. X is equal to 3 plus or minus the square root of 29 over 2. Now, when you go to list this on the test, what I'm going to look for is you to leave your answer in simplest radical form. 29 can't be broken down. So when you list the 0, you could list it like this. Remember, as in x-intercept, you list it as an ordered pair. So 3 minus the square root of 29 over 2, comma 0. 3 plus the square root of 29 over 2, comma 0. And the one that we did synthetic with. And remember, that's going to be 1, comma 0. Now, if it asks you to list the factors are going to be that one that you did synthetic with, so x minus 1, and then the other factor would be that quadratic equation. And these would be the factors of this polynomial. Now my y-intercept is just that 5, but again, you could plug in x equals 0. Now, if you want to see that your x-intercepts, where you're going to place them, we're going to approximate the square root of 29, and it's about 5.4. So when I do this problem here, it'll be 3 minus 5.4 divided by 2. And then that's going to give me negative 2.4 divided by 2. And that'll give me negative 1.2 comma 0. And this will be 3 plus 5.4 divided by 2. So 8.4 divided by 2. And this will give me 4.2 comma 0. So this is where my x-intercepts are going to be. And again, you're going to have to graph these radicals. So you are going to have to approximate it. Now, I'm going to show you when you key it into Desmos what it's going to look like, or even on your graphing calculator. It's not going to show you the radical form. It's going to give you the crazy long decimal. If you list that as a 0, crazy decimal, or as an x-intercept, you will get it wrong. You must do synthetic. You must use quadratic formula to get it into radical form. So let me go ahead now and let's graph this and add in our M behavior. So I'm going to graph the negative 1.2. My other 0 was 1, and my other 0 was about 4.2. Remember your M behavior, falling to the left, rising to the right. Your x-intercept was at positive 5. So let's say I change these to go by 2s. So there's your y-intercept. And then if I do the same thing here, 2, 4, 6, 8, 10, I'm going to go ahead and I need to get some additional points. This would be 12. These are all negatives. So now, for this connection that's right here, I could just connect it to the y-intercept. And then I need to come here because I know it's crossing through. But I need to find an additional 0 in this section. So I'm going to do synthetic with a 2 to get an additional, actually with a 3 to get an additional point. And that should have been moved over just a tad. So 4.2 is here. And it's going here. So I'm going to plug in a 3. You could have plugged in a 2. It doesn't really matter. But let's do synthetic with 3 to get the additional point. So 1, negative 4, negative 2, 5. Bring down. Multiply. Add the column. Multiply. Add the column. Multiply, add the column. So my additional ordered pair is 3, negative 10. So then I can put a point right here. So 1, 2, 3, and the 10. Come on down, and then back up. Now let me show you the Desmos graph. So this is graphing it by hand. Okay, so I do not have a screenshot of the Desmos graph, but this is what the graph looks like. And this is how you would have to handle it. You would find your zeros. Even if they're irrational, you're going to have to approximate it to know precisely where to put those x-intercepts. But again, do not list the x-intercepts or the zeros as decimals. You're just using that for your graphing purposes. You will list them in simplest radical form. I'm going to skip over example 6. I'm going to go right into example 7. So this is the Desmos graph for example 7, which I'm going to work out on the next slide. So just so you can compare, you can go back and forth from the slides to see how close my graph ends up looking. So example 7 is already in factored form. So I don't have to do any synthetic. I just take each of my factors, set them all equal to 0 to get my zeros. And notice these two are the same. So really I'm only solving 2 things here. Add 3 to both sides. This is the easy way when it's already factored for you. Now to determine my end behavior, I have to go back and count how many zeros I actually have. So there's 2 from this one, 1 from this one, and 2 from this. So I have a total of 2 plus 1 plus 2, I'm going to have 5 zeros. So this is based on, and it's a negative number in front here, so a negative x to the 5th. So when it's a negative x to the 5th, rise left, fall right. So now, notice this one, the x equals -1. This one occurs 3 times. It's got an odd multiplicity. This one occurs 2 times. So it's got an even multiplicity. So this one is going to be a touch and turn, or a bounce, however you want to think of it. And this one's going to cross. So let me go ahead and add in these zeros. So -1, and then +3. I could also find my y-intercept. Now this time it's not in that form where it's just the constant. I actually have to set x equal to 0 to get my y-intercept. So 0 minus 3 squared times 0 plus 1 times 0 plus 1 squared. And it's going to give me my y-intercept. And then 1, and then 1 squared. So this will give me negative, and that's a +9, and these are just 1s. So then my y-intercept is the ordered pair 0, -9. So it's actually going to go off my graph. So maybe about here is my y-intercept. So remember, my end behavior was rising to the left and falling to the right. So I can already see that when I go to connect this, it's going to hit my y-axis. I need to find an additional 0 in this section. So this time I'm not going to do synthetic. I just have to plug in a number. So my additional point, I'm going to let x equal 2. You could plug in a 1. Doesn't really matter. So if I plug in 2 to the original problem, 2 minus 3 squared, 2 plus 1, 2 plus 1 squared, it's going to give me a y value, -1 squared, 3 squared. This gives me 1, 3, 9, and this is going to give me -27. So 2 comma -27, way off the graph. So this was a good thing I plugged that in, because now I know from this y-intercept, it's going down. It's going to go down somewhere down here, and this would be the ordered pair to -27. So it'll come down here, and then it'll come on up to the 0. And then it'll do a touch and turn, and then go in the other direction. Next, this one is also factored for me. So again, I could look to see how many factors I'm going to have. I've got a 2 and a 2, so 2 plus 2. It's going to be based on a negative x to the 4th. So my end behavior will be falling left and falling right, sort of like the reflected parabola. So again, take each of your factors, set them equal to 0, solve for x. So my first 0 is at -2. And then +3. Remember, both of these occur 2 times, making that an even multiplicity. So again, it's going to be the touch and turn. It's not going to cross over the x-axis at those coordinates. Now let me go ahead and find my y-intercept. So for your y-intercept, because it's not, it's already in factored form, I actually have to set x equal to 0. So in my original problem, negative sign, 0 plus 2 squared, 0 minus 3 squared. This gives me negative sign, then 2 squared, -3 squared, 4 times 9, -36. So So my y-intercept is 0, negative 36. It's going to go way off the graph. So let's go ahead and put these zeros on the graph. So I have one at negative 2, positive 3, and then I also have the one at the negative 36. So way down here, let's just say it's here. So now what I need to do is, remember it's a touch and turn. Let me go ahead and add in the end behavior. Falling left, falling right. So remember it's a touch and turn. So what it's probably doing is it's coming down here, touching the Y, and then I could go ahead and find an additional order pair in this section just to see where it's going, if it's going lower or higher. So let me go ahead and let me plug in x equals 2 to the original. So a negative sign, 2 plus 2 squared, 2 minus 3 squared, 4 squared, negative 1 squared, and I get negative 16. So then 2 comma negative 16. So somewhere up this way a bit, because this was at negative 36. So it's obviously coming back up and coming to that 0. And the previous slide had the Desmos. Actually, it's the next slide that has the Desmos graph. So let's see how close it came. So here is the graph of the previous function. And again, notice it's falling to the left, falling to the right. Here was my y-intercept. Now, here is plugging in a 0.5. So here, notice it was the negative 39. So it did go a little bit below. It did dip below the y-intercept. But again, I just want to see the general direction of how your graph is going to go. And I'm only going to do one more example in this video to show you that you can get imaginary zeros. So this potentially could be a calculator question or even a non-calculator, because let's list our possible zeros here. My possible zeros, my factors of my last term, 7. So positive and negative 1, positive and negative 7. First term is just a 1. So it's negative 1, positive 1, negative 7, positive 7. So let me go ahead and do synthetic. Now, if it were a calculator question, even though it's an x to the third, we need 3 zeros. But if you key this in your calculator, you're going to only see it hitting the x-axis one time, and it's going to hit it at negative 1. Then that should be a clue that your other 2 zeros are going to be imaginary solutions. So let's go ahead and do it. Put in the coefficients, bring down, multiply, add the column, multiply, add the column, multiply, and we get a remainder of 0. So then now let's make it into a quadratic equation. It can not be factored. There are no factors of 7 that give me 5. So quadratic formula. So if it asks you to list the factors are going to be x plus 1 and x squared plus 5x plus 7. These are the factors. However, quadratic formula, negative 5 plus or minus 5 squared, 4 times 1 times 7, 2 times 1. Simplify what's under the radical. And x is equal to negative 5 plus or minus square root of negative 3 over 2. Negative 5 plus or minus I radical 3 over 2. Now, this is not an x-intercept, but it is one of the zeros. So where it says to list your zeros, you have a 0 at x equals negative 1, x equals negative 5 minus I radical 3 over 2, and x equals negative 5 plus I radical 3 over 2. These are the zeros. However, the only x-intercept you have is -1, comma 0. So if I graph this, I'm going to graph my 1, 0. I'm going to graph my 1, 2, 3, 4, 5, 6, 7, my y-intercept, and the graph is going to look like this. Because remember, your M behavior was supposed to have fallen left, rising right. So in order to get to the right, we're going to be going up. So there's only one x-intercept, but there are still 3 zeros. And the y-intercept was just that constant, 0, comma 7. So the rest of the examples say to use a graphing utility. So I will finish up these examples on Wednesday, showing you how to use your graphing calculator.